So in the next video, we're going to have a infinite long piece of wire that has a charge on its surface. So we're going to put it in a cylindrically shaped Gaussian surface. So you can imagine the wire coming in this end and coming out this end so that our cylindrical Gaussian surface encapsulates it. So the field lines are going to come off of the surface of the charge distribution, and if this was a little bit better of a demo, all these toothpicks would be coming out straight perpendicular to the surface. Unfortunately, it's got a little squished over the years. But you can see here that the surface area that we need to calculate the electric flux over is essentially the surface of the tube that makes up the cylinder and not the end cap. So we don't include the end cap. So it's not the full surface area of a cylinder. So in this example problem, we have an electric field strength due to an infinite line of charge is measured at 250 newtons per coulomb at a radial distance of 5 millimeters away. And we want to know how much charge is in the length of 3 millimeters of the line of charge. So we're going to get out Gauss's law, the idea that the flux is equal to the electric field dotted with the area, which is equal to Q enclosed divided by epsilon naught. So we're not going to worry about the electric flux since we're not asked to calculate that. We're going to worry about this here. So the electric field is given in the problem, but the area that the electric field is actually going through is going to be the body of the cylinder, just as I showed you in the video I preempted with at the start of this. This means essentially when you're dealing with that, you can unroll that and it becomes a rectangle where one side of the rectangle is the original circumference of the cylinder, so 2 pi r, and then the other half, so the 2 pi r is here, and then you have your length here. So that area is 2 pi r times L. So you're given r in the problem, that's your 5 millimeters, and you're given L in the problem, that's your 3 millimeters. And our goal is to find the charge enclosed, and then remember epsilon naught is the electric constant, the 8.854 times 10 to the minus 12 coulomb squared per Newton meter squared. So that gives us a Q enclosed of 6.26 times 10 to the minus 13 coulombs.